Welcome back. This is the second video of section 3.1 in which we are going to talk about 2 points. The first point is about the closed set formulation of compactness, and the second point is about compactness of subsets of a topological space, because the whole space need not be compact, but it may contain compact sets. Okay, first point. As you know, when we take the complement of a set, we transform an open set into a closed set and vice versa, and we transform a union into an intersection. Okay, so therefore there should be an equivalent formulation or definition of compactness in terms of closed sets and intersections. Okay, so this leads us to the following definition. We say that a collection of sets f lambda has the finite intersection property if any finite intersection of these sets is not empty. Okay, so I'm not saying that the whole intersection is not empty. So this is the point here, actually, because let me give an example. If we consider the collection of sets f lambda, which are lambda plus infinity, well, this collection has the finite intersection property. Why? Because if I intersect f lambda 1 with f lambda 2 with f lambda n, when does a point belong to this intersection? It belongs to this intersection if and only if it's bigger or equal than any lambda I. So this happens if and only if it's bigger or equal than the maximum. So the whole intersection, as you know, is an interval, and this is not empty. Okay. However, the whole intersection here is empty because there's no number bigger than all other real numbers lambda. Okay. So in general, if the whole intersection is not empty, then any finite intersection is not empty because this is smaller. Okay, the whole intersection is contained in any finite intersection. Okay, but the converse, as we saw, need not be true. However, it is true in compact if f lambda are closed sets and you are dealing with a compact space. Okay, so this is the point. Okay, so a space is compact if and only if for every collection f lambda of closed sets having the finite intersection property, the whole intersection is not empty. Okay, so this was not the case in our previous example. Why? Because R is not compact. Okay. So we have to prove there are two implications. So I will just prove one of them, and the other one is just completely symmetric. So I will assume that X has this property that the whole intersection is not empty whenever the collection of closed sets has the finite intersection property. Okay, and I want to prove that X is compact according to our definition of last time. So for this, I go back to the definition and I consider an arbitrary open covering of X. Okay, now therefore X without the union is empty, but the complement of the union is the intersection of the complements. So this is De Morgan's law. So the intersection of these sets is empty. And now if O lambda is open, then the complement that I can call f lambda is now closed. Okay. So the whole intersection of lambda is empty. Therefore, according to our assumption, f lambda, the collection f lambda, cannot possess the finite intersection property. And therefore, there must be a finite subcollection whose intersection is empty. Okay. It's by contraposition. So there is a finite subset J of L such that the intersection over lambda and J of f lambda is empty. Okay, and once again, the intersection of the complements is the complement of the union. So therefore, X can be written as the union of these O lambda for lambda and J, and therefore we started from an arbitrary open covering and we extracted from it a finite subcovering, and this is just compactness. And now the converse is just symmetric. You can go back through the steps. Okay, start with the union and etc. So it's completely symmetric. So, and as a corollary, as a particular case, if we have a decreasing sequence of non-empty closed sets of a topological space, then the whole intersection is not empty. Why? Because a decreasing sequence of non-empty closed sets has the finite intersection property, because if I intersect fn1 with fn2 with fnk, this is decreasing. So the intersection corresponds to the smallest set, which corresponds to the biggest index because it's decreasing. So the intersection is just f of the maximum, and by assumption each set is not empty, so the intersection is not empty. And according to what you said, the whole intersection is not empty. Okay. So this concludes the first point about closed set formulation of compactness. Now I move to the second point about subspaces. Now, as you know, a topological space need not be compact, but it may contain compact sets. So we want to give a characterization how to detect, how to prove that a subset is compact. Okay. So here's the definition. So first I need to extend the notion of covering a little bit. So in the previous video we said that a collection covers the space if the union is equal to the space. But we can extend it a little bit. If we have now a subset of a topological space X, a covering of Y by subsets of X means that the union of these sets contains Y, not necessarily equal, but it contains. Okay. So this is a slight extension of the first definition. Now, these two definitions are equivalent actually. Why? Because if we have equality, equality is a particular case of inclusion. So definition 1 is a particular case of this more general definition. But conversely, if we have a covering of Y by subsets of Y according to the second definition, then this means that Y is contained in the union. But since O lambda is a subset of Y, then the union is also a subset of Y. So we have equality actually. So Y is precisely equal to the union. Okay, so therefore we recover definition 1 in this case. Okay, so it should be from the context. What do we mean by covering? But covering means that union contains. Okay, and it will be clear actually later when sometimes we have equality. Okay, so this means that there's no contradiction between the two definitions, but we should be precise. We should be precise when we say covering by open sets of X or open sets of Y. Okay. Okay, so now we have slightly two different conditions. Okay, consider this condition. Every covering of Y by open subsets of Y has a finite subcovering. Okay, this is the definition of compactness of Y. So whenever Y is a union of U lambda and U lambda open in Y, then Y is a finite union of these sets. Okay, and consider the second another condition. Every covering of Y by open subsets of X has a finite subcovering, which means that if Y is contained in the union of O lambda and each O lambda is open in X, then Y is contained in O lambda 1 union O lambda 2 union O lambda 2. Okay. Now, these two conditions may seem different, but actually they are equivalent. And this follows from the definition of the subspace topology. Okay, so the two conditions above are equivalent actually, and they both characterize compactness. Okay, so we just prove two implies one, and the other way is just symmetric. Actually, you can prove it, and I encourage you to do it on your own to test your understanding. So suppose that condition 2 holds, and I want to prove condition 1. So I go back to the condition. So I take a covering of Y by open sets in Y. Okay. Now, what does it mean that U lambda is open in Y? It means that by definition, or by what we did in chapter 1, that U lambda is the intersection of Y with an open set of X. Okay, we proved that. Actually, this was the definition of the subspace topology, if you like. So therefore, since U lambda covers Y, so Y according to the first definition, so Y equal to union of O lambda, and now I replace U lambda by its value, and by distributivity of intersection with respect to union, I can put the Y outside, so I get Y intersected with the union. And now, from set theory, this means that Y is contained in the union of O lambda. Okay, why? Because if X is in Y, then X is in Y and in the union, so X is in the union. This set theory. So therefore, now, so we have now a covering of Y by open sets of X, and condition 2 that I assume tells me that I can extract from this covering a finite subcovering So finitely many O lambda cover Y, and therefore when I take the intersection of Y with Y and this union, and I use distributivity, the distributive rule, so I get Y intersected with O lambda 1 just U lambda 1, Y intersected with O lambda 2, U lambda 2, and so on. So finally I get Y is exactly equal to U lambda 1 union, etc. union U lambda n. Okay. So this proves that condition 2 implies the compactness condition, and the other implication is just the reversed implication, just symmetric. Okay. So when we want to prove that a compact a subset of a topological space is compact, instead of taking a covering by open set of the subset, we can take a covering by open sets of the bigger space, okay, which is sometimes easier to deal with. Okay, so now, so I will end this part with two results. The first one saying that every closed set of a compact space is compact, and this follows from the definition actually. So, and this is a good exercise in proving. So it illustrates how to prove that a set is compact. So we take now a covering of Y by open subsets of X, as we know from the previous lemma, and we want to find a finite subcovering. Now we add to this covering the complement of Y. Since Y is closed, the complement is open. Okay, and now, so therefore I get a new collection, if you like, O lambda. Lambda belongs to the original index set L union an element not in L, equal mu. So I add to my original covering an extra term. So I have now actually a covering of X of the whole space. Okay, because union of O lambda contains Y, and X minus Y is the complement. So union of O lambda union the complement contains the whole space. So now we have an open covering of the whole space, and compactness tells me that I can extract from it a finite subcovering. So there is a finite subset J in L union mu, whose union cover is equal to X in this case. So when I remove from this finite covering X minus Y, I get a finite subcollection that covers Y. Okay, because X minus Y does not cover Y, so I can remove it actually. So I started from, of course, if J is finite, when I remove the point, an element is still finite. So, okay, so this is the first result, and the second result is that every compact subset of a metric space is closed in this space. Okay, now here, so far I didn't need the assumption of a metric space, but here I need it because in a metric space we can separate two distinct points by disjoint balls, and we did that in the exercise. So we need an extra assumption on the space. So it's not true in any topological space actually. Okay, and we'll see why. So consider. So when I don't need the metrizability, the properties of a distance, when the properties of a distance are irrelevant to the discussion, then I just can work with general topological spaces. Okay, but metric spaces have something particular, and sometimes it's needed. Okay, and sometimes working in a metric space simplifies the discussion, but sometimes it's irrelevant. Okay, so we have a metric space X and a subset K of X that we assume that to be compact. We have to prove that K is closed on X. How do I prove that? We usually have two strategies. Either we go back to the definition and prove that the complement is open, or we prove that it's equal to its closure. But here, let us prove that the complement is open. But how do I prove that a set is open? One way is to prove that it is a neighborhood of all its points, according to our definition of neighborhood. So I pick a point X in the complement of K. And now, so X is not in K and Y is in K. You can draw a picture if you like. So take Y in K and X outside. And now this is where the assumption plays a role. if x is different, so if x is not in K and y is in K, then necessarily x is different from y. Okay. And since we are working in a metric space, we can separate x from y by disjoint poles. Okay, so there is a neighborhood that I call u sub y, because I will let vary y now. So I fix x here actually. So there is a pole that I call uy of center x, and the pole vy of center y that are disjoint. Okay, so I can separate the points by two disjoint neighborhoods. And now, when y varies in K, it's clear that K is contained in the union of Vy, because if I take y in K, then by definition y is in Vy, because Vy is a neighborhood of y. So this is so I have now a covering of K by open subsets of X, and compactness tells me that K is covered by finitely many Vyi. And now I take U to be the intersection of Uy1, because now remember that Uy1 is disjoint from Vy1, Uy2 disjoint from Vy2, and so on. So when I take the whole intersection of these, this is a finite intersection of open neighborhoods of X, and therefore it's an open set, so it's still a neighborhood of X. So this neighborhood of X does not intersect K, because it does not intersect any does not intersect Vy, because it's contained in Uy1. Does not intersect Vy2, because it's contained in Uy2. So U does not intersect this union. Okay, so it does not intersect K, and therefore it's contained in the complement of K. So we started from an arbitrary point in the complement of K, and we found an open set containing X and contained in X without K. And this proves that X without K is a neighborhood of X. Since X was arbitrary, this means that X without K is open, and therefore X is closed. So we don't need the full assumption that it's symmetric space. We just need this condition that we can separate two distinct points by disjoint open sets or by disjoint neighborhoods. And if you want to know, this property is called the Hausdorff condition, okay, that you will learn next year. So this concludes this part, the second part of section 3.1, and I will finish this section in the next video. So thank you for your attention, and see you next time.